We're live. So, in theory, yeah. So YouTubers are having to choose. So imagine, like for me, it's not that complicated, right? Like obviously, the stuff I do on YouTube is not targeted towards children,
Right.
so I don't have to worry. I'm safe to say that my content is not for children, but um, that if and not really worry that the FTC will come along and look at it and say, oh no, you're absolutely creating, there's animated characters and you are creating content that is for children, right?
Oh,
So for me it's not a problem. But imagine you're like say you make Lego on YouTube and you're doing
right.
like you build the Apollo lander.
Yeah.
So that is not the kind of Lego that little kids are going to want to get access to, and yet you are doing something. It's a toy. What if you're showing action figures in your stuff? What if you're reviewing games? What if you're playing Minecraft? And so if you
Yeah.
and there's lots of adults that play Minecraft. What if you're
Right.
reviewing I don't know, the season 3 of The Dragon Prince?
Yeah.
So, um, so it's causing of this existential crisis for a lot of people in the YouTube community because if they get it wrong and the FTC comes along and slaps them with a penalty with a fine, it's a 42,000 fine. It's an existential event. It is a and if you have 1,000 videos and it decides, then you have a $42 million fine from the FTC, right? I have 1,000 videos on my channel. So, um, so a lot of YouTubers are they're going to pick safe for children or for children, even though it's their content isn't. And if they do that, then they suffer enormous restrictions on the YouTube platform. So uh, it is one of I think it is probably the most, it's the biggest problem that YouTube has faced so far. I think there has not been a crisis of this scale for the vast majority of YouTubers. And I do not envy, like for the people who make stuff for kids,
Yeah.
they, and they were enjoying a free ride where they were being able to
Right.
advertise to children. They knew what they were doing was skirting the issue. Ryan's toy review, all these people, I think they recognize that these changes were coming. But
Right.
for the vast majority of the people who are just in between, if you're showing Kerbal Space Program, right? My
Yeah.
kids liked to watch Minecraft videos when they were 11 years old,
Right.
with my agreement, right, as a
Well,
parent.
I learned about PewDiePie from a 9-year-old, and
Yeah,
I don't think PewDiePie is exactly appropriate for 9-year-olds,
yeah,
but
yeah, yeah.
a
So
video gamer.
this is a big deal. This is a really big deal, and there's no simple solution for anyone who is in any way in a gray area in between. And I think
Yeah.
what is defined as child. The guy who cuts up stuff to see what's inside. They have like a big saw blade and they slice various things open.
Yeah.
And and
Or even like our friends over at Smarter Every Day.
yeah,
What's Dustin gonna do?
yeah.
Because
Sometimes
that's
he'll
his
have his kids in
living.
his videos and he's doing
Right.
demonstrations to show how things work. So yeah, there we are. Here we are. Welcome to the future. So again, Astronomy Cast, not targeted towards children.
No.
So I mean, it's not. But it's family safe.
Yeah.
One of us tries to not swear on a regular basis.
I'm sorry.
The other swears like a sailor.
I don't mean to.
I'm going to say hi to some people. Hello to Andy Cowley, Beatrix Lidner, Ben Kalo, Dusty Reichwin, George Lancaster, Greg Nickel, Guido Bibra, James Aberson, Janelle Duncan, Jason Elric, John Seffel, Johnny J, Linda Sadiq, Michael Bear, Michael Meyer, Nicholas B, Ocean McIntyre, Paranor R. Instro, Rich Wilson, Thomas Sepstrup, Wayne Johnson, Yamagashi-san, and Zap Van Zap. And hey, everybody. Welcome. to this double episode of Astronomy Cast. So we are going to record this episode, and then we are going to shut the whole party down, and then we're going to start it up again and continue the second part to this episode. So today we're going to talk about stellar nucleosynthesis, and then today, later on today, I haven't written my intro for the second part yet. Okay, there will be a slight break in between about a 1 minute break between when we shut this one down and then when we start up the other one. Okay.
Oh, Michael just said something rather horrifying. He said you could try and take out someone else's channel by sending children to watch it.
Yeah, this is a nightmare.
You could destroy someone simply by adding their site to a top 10 sites for kids.
Yeah. Well, I mean, the hope is that when the FTC reviews a channel, they're going to be looking for people that are doing egregious violations of that they are saying that their stuff is not for kids, and yet they are absolutely targeting children and attempting to profit off of it. Like, that's the hope, is that's what they're going to go after. But a lot of people are super worried, and the consequences are so dire that everyone is going to err on the side of caution. And so what it's going to cause is it's going to cause just this vacuum of content. Educational content, who wants to take that risk? And then therefore, it's going to be Disney Plus. Right? Disney Plus is what wins, because every parent is going to be fine to just throw their kid in front of Disney Plus and let Disney Plus roll on with hilarious animated cartoons and Hannah Montana.
And really bad movies from our childhood.
From our childhood, exactly.
Strangely look forward to watching.
As opposed to really good content that's still very appropriate for children.
Yeah.
On YouTube, educational content, things like that. So, not great. Like I said, again, I don't feel like we are in any way at risk of this. But then again, not a lawyer. Maybe we should talk to a lawyer and see what changes we can make. So anyway, because we are educational.
Yeah. Susie is wondering where you put your show intro.
I put it in the Trello. I haven't saved it yet.
That would be why she can't find it.
There, it's saved, Susie.
Okay.
Enjoy. Okay. Are we ready to go?
Yes.
Okay.
I hate everything.
Yep. It's one of those days.
And I have the yawns because it's Friday.
Yeah. Sleepy Pamela.
Okay. Well, I'm surrounded by sleeping dogs, and it's just somehow inspiring.
There is a rule.
Okay. I'm ready to press record whenever you are.
I'm ready too. I pressed it. I did it.
Mine said I need a file name. 546.
548.
548. Okay, I'm recording.
Okay. I am also pressing record. Pressed record. I am also pressing record. All right. Astronomy Cast, episode 548. Stellar Nucleosynthesis Revisited, Part 1. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. I read that intro in an excited way to wake you up. Wake up!
It's the last Friday before a week-long vacation, and my body's like, tomorrow you can sleep in. Can we start now?
I think you need to check the calendar because, as always, Thanksgiving happened a month ago. We have
We're just
all,
always behind the ball here in the lower 48.
yeah, yeah. We in Canada we already did it, so try to catch up. Now we're actually recording 2 episodes today, but we will release them slowly and carefully over the next 2 weeks. Where are you off to? Is it just for the holiday, or you got plans?
I am doing Friendsgiving out in California. I'm going to see our good friend David Joseph Wesley, who's responsible for the music at the beginning of each episode. And we're going to go ride the Millennium Falcon at Galaxy's Edge
Oh,
because that's how you celebrate the holidays.
that is going to be so great. I would love to go back to Disneyland and see the new Star Wars stuff. Even though I have a very low key relationship with Star Wars these days, I think my childhood nostalgia is now, I finally just wiped out all childhood nostalgia for Star Wars, or maybe the Star Wars, the over, monetization and release schedule of Star Wars has finally destroyed my childhood love of Star Wars. But I would love to try all that stuff. That sounds pretty great. So you got to let me know how it works.
I totally will. And you can follow along on Instagram because I suspect there will be pictures.
Now, The Expanse season 4, though,
Starts December 12th, which is my
I
birthday.
know. I'm so excited. The universe started out with hydrogen and helium and a few other elements, but all around us there are other, more proton rich elements. We believe these heavier elements formed in stars, but which stars and at what points in their lives? Today we'll update our knowledge with the latest science. Pamela, the fact that there are certain amounts of hydrogen and helium with trace amounts of lithium, this is one of the best indications that the Big Bang is a thing. And
It
yet,
is.
and yet, I'm sitting on a chair surrounded by a house, living on a planet, and there's not as much hydrogen, helium, and trace amounts of lithium in all of these things. And so these heavier elements had to come from somewhere.
Exactly. Exactly. And this is actually a story that usually gets simplified far more than it should. And over the past few years, different things keep coming up during our show that require us to realize that nucleosynthesis isn't just something that happens in the cores of stars. It isn't just something that occurs when stars explode. It's something that occurs in all sorts of weird and awesome places that lead to, well, hydrogen 3, sorry, that lead to helium 3 on the moon and, well, to weird and esoteric elements like technetium in the atmospheres of stars. And I thought, well, it was time to come back and fill in some of the gaps that we left when we tried and crammed all of nucleosynthesis into one episode in the past.
And do you remember how long ago it was that we covered nucleosynthesis? It was a long time ago.
I want to say it was somewhere around year 1 or 2.
Yeah. It would
So,
have been one of the
yeah,
topics that we would have gone after early on. And there have been events and there has been new knowledge that has updated the whole process. And you think so much that it's a two-parter. So 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 let's dig in. So where do you want to, which parts of it do you want to cover today?
so I think that we start with the Big Bang and we end with the death of a non exploding star and get all the nucleosynthesis that occurs in those places.
Okay, all right. So let's start with the Big Bang then.
So, initially, as we've talked about a bunch in these episodes, our universe was just a big old ball of energy. And as that energy expanded and cooled and expanded and cooled, less than 3 minutes after its start, our entire universe was similar in conditions to the inside of a star. Now, it wasn't identical. We didn't have the same kinds of reactions that happen in stars, but the energy, the density, the temperature of everything that was present was such that hydrogen atom cores, so protons, were able to come into existence. And these protons collided with one another, we were able to get helium, we were able to get some lithium, we were able to get some beryllium. Electrons weren't really bothered at this point because it was just a soup of hot ionized everything.
Now,
But
I
it
want to
got
make
us
just like
somewhere.
one quick sort of distinction here. So, I mean, you said that it's a ball of energy, and that's a bit of a misnomer, just because it could have gone on forever. It could have been infinite in all directions, just highly
Right.
dense, right? Just this.
Yes, that's true. I as a slip of the tongue
Yeah.
because it was convenient, gave our universe shape. We
Yes.
don't know if our universe has a finite to it. If it does, we're a four-dimensional hypertoroid, which is a donut, not a
Right.
ball. Um, but we were basically a big old something.
Right, right. Something that could have been fun. It could have gone on forever. And when we think about a star, right, we imagine the gravity is pulling in on the star, the light pressure is pushing out on the star, and and that balance creates the shape of the star. And yet, at the very core of the star, you've got the place where the magic happens, where the fusion is going on, and it is because these atoms of hydrogen are mashed together so tightly and at high temperature that you get this fusion. And so how was you said it wasn't exactly the same as what's going on in a star, and I kind of imagine it like it was rushing through this phase from whatever came before when it was just like this quark gluon plasma to expanding galaxies moving away from each other. There was this transition point, and that's when all that magic happened. How was it different?
Well, in the early universe, you had a P process, proton process buildup that allowed you to get that lithium and beryllium. In the centers of stars, you don't have this. Instead, what you have is the proton-proton chain that allows you to get from one kind of hydrogen to other kinds of hydrogen and eventually up to helium. But then it skips up to carbon. And so because we have different temperatures, different densities in the cores of stars, this constant splay of protons, which is what basically the entire early universe was, well, we don't have that in the cores of stars. So without the rapid flux of protons onto atoms, you don't end up building up lithium and beryllium in the same way.
Right. And so, I mean, there are multiple ways that heavier elements get built up, and the environment of what's going on defines whether protons are being mashed together and turned into helium, or as you mentioned, this other chain. So okay, so you've got this time. How long do we know about how long this was going on for?
It was, I'm sorry, my puppy is losing her mind. It's, stop, just stop. I need to let her out of here. She's going to lose it. Hold
Yeah,
on.
fine. Susie can edit this out.
Go. There was like leaves moving or something.
Right, needs to be examined.
So all the exciting parts of our universe, from the moment of expansion that was the inflationary epoch through to Big Bang nucleosynthesis, all of that was over by the end of 3 minutes.
Wow.
So, yeah, it was super brief to basically get us to everything we have today.
And if it had lasted longer, then would we see more, say, lithium and beryllium in the universe and helium, like a
Yes.
different quantities, different ratios?
Yes, the ratios that we see do help constrain what the process was and tell us that our understanding of the Big Bang is a realistic one. So when we
Right.
talk about the Big Bang, it includes this Big Bang nucleosynthesis.
That's incredible. I mean, it's incredible that you measure the ratios of these elements in the universe, and then that tells you how long the universe was behaving like a star. And it
And
wasn't long.
and this is one of the amazing things about our universe is the physics works the same no matter how you put stuff together. And so during the Big Bang, we had high energies, we had a massive flux of protons, we were able to build up heavier elements. Now, as we look around our universe, we still see the periodic influx of protons with sufficiently high energies that we're able to, well, build these elements again. Except here, what we're looking at is cosmic rays and cosmic ray spallation being responsible for processes that in the past only occurred during the Big Bang. So we still have a negligible buildup of lithium and beryllium that occurs from that occurs from cosmic rays hitting other particles and building up or splitting things apart and breaking down to get us to these atoms.
That's really cool. And so even though we can't look at the Big Bang directly, we can watch as cosmic rays impact detectors, impact the planet, and produce the same cascade of particles, and you can see that exact same process happening.
And the way we often figure out what's going on is we simply look around and we go, that thing that doesn't match expectations based on our bad prior understanding. And so we have to upgrade our understanding to match what we see. So in the case of nucleosynthesis, our understanding came from the fact that we looked at the sun and we looked at geology, and we couldn't explain how the sun had existed for so long given all of the energy generation mechanisms we understood. People did crazy calculations like figuring out how much total energy and how long could the sun burn for if it was made of something that functioned like coal,
Yeah, right.
and that doesn't work.
It was
So
a
they
valiant
needed,
effort.
it was a valiant effort, but the amount of energy released in such inefficient processes as burning organics, which is what you're doing with coal, that can't power a star for the geologic times that we were beginning to realize had existed. So, in the early 1900s, with the advent of quantum mechanics, with advances in electromagnetism, with the beginning of general relativity, we also saw nuclear fusion coming out all at once. All of these understandings just arising in a few short decades. And it changed how we look at our sun, allowing us to see that in main sequence stars, another thing that was being figured out at the same period in time, gravity crushes down the star and it gets supported outwards by light pressure. These are the equations of hydrostatic equilibrium. Chandrasekhar has some of the best explanations of this. And you can figure out for each combination of radius and mass what the internal density will be, what the internal temperature will be, and what nuclear actions that allows to happen.
Right. And so then, you had mentioned sort of earlier on that there are different kinds of nuclear reactions going on at the cores of stars than the kinds that we see, that we would have seen at the beginning of the universe.
Right. So we start off with simple things like the proton-proton chain, and this allows us to build up where we're getting hydrogen, we can get carbon, nitrogen, and oxygen, we can get helium. And sorry, from the I'm mixing chains. Susie, you're going to have to edit that. I screwed up because I read the wrong notes. So we start off with the proton-proton chain, and this is where we slam together two helium atoms. We're able to get off two hydrogens and a helium-4, and that helium that we started with going into that final result that gives us the helium-4, which is stable. That started with, we paired together two hydrogens. They gave us a deuterium and a regular hydrogen. And deuterium is a hydrogen with a neutron. We then collided those together. We got helium 3. We combined those helium 3s. We got a stable element. And one of the defining characteristics of nucleosynthesis is we're going from something that was stable and hanging around and able to get heated up and compressed through quite often really unstable, short lived
Right.
things. And then we're eventually building to something stable. And that helium 4 atom, that is stable. And
It,
once you have that, you're able to start doing even more.
it must have been, that must have been a real puzzle, right? That you think about, like if you sit down and try to figure out the math, the particle physics math, and you take your hydrogen atoms and you try fusing them together into more complicated things like a stable helium, you can't get there from here. That the outcomes won't be stable, and so it must have been an incredible leap of imagination to say, okay, so maybe there are a bunch of intermediate unstable forms that are being pushed together, and those are then turning into the stable forms that we're familiar with to get from
And
hydrogen to helium.
and additional leaps were also needed where they had to figure out, okay, why is it that these things that have proton rich cores and should be repelling each other, how is it that they can finally get close enough? How is it that we can overcome these different forces? Where are those pockets of allowed reactions where we can overcome the repulsive forces, where we can get new things into the nuclei, and we can allow these processes to happen? That particular helium 4, that is a really annoying atom to try and get past because it is so stable. And this is where you really need to have a significant burning process already in place before you can start, well, building it up into other things as well. Yeah, helium 4 wants to stay helium 4. It's annoying that way.
Right, right. And so ideally, it would degrade, and then you would have a transition that you could then use to go to a heavier element.
And we just don't have this, and this is where instead what we have to start looking at is what are the cores of stars seeded with. This is where we start looking at, is there any existing carbon around that can have nuclear reactions with hydrogen? Once you can get carbon and hydrogen going together, now you're producing nitrogen, which produces more carbon. That carbon can then produce more nitrogen. And you just have this ongoing cycle of carbon, nitrogen, and oxygen that's just building and building, releasing more elements as it goes.
And does that happen inside a star like the sun, or does it have to be a heavier star?
This can happen in stars like the sun.
Okay.
And what's cool is it couldn't happen in that first generation of stars because there wasn't the
Right.
hydrogen, there wasn't the carbon to seed this particular cycle.
So it's, I mean, it's kind of like a catalyst in another kind of reaction where you can't have the reaction without the catalyst. And so once you were able to get that carbon from some other, the death of other stars, then that could seed these stars and they could help with that. That's really interesting. I like that.
And our sun doesn't currently have this reaction going on, just to be clear. This is something that can happen later if its core heats up, which is possible later on. Um, but when you have bigger stars, stars that are 1.3, 1.4 times the mass of our sun, their core is actually dominated by this process when they're on the main sequence. So when we talk about main sequence stars burning hydrogen in their core, we're talking about the majority by number, but not the majority by type, because there's a whole lot of bigger stars out there.
Right, right. And I mean, I think where this whole conversation is going is just the fact, as that I mentioned earlier on, right, which is that I'm made of meat. I'm sitting on a chair. I'm in a house. The house is made of carbon. I'm breathing an atmosphere made of nitrogen, right? All of these heavier elements. So how do they get out of the star? Because why doesn't the star just, there's a lot of gravity going on, and when the star dies, why doesn't it just hang on to all of it and then we never get it?
Well, we're dealing with a bunch of different processes here. So, I first of all, stars like our own sun they're eventually going to run out of fuel in their core, and the core is going to quietly collapse down into a white dwarf while the outer atmosphere puffs off. And through various dredging processes, mixing processes, you can churn up material from deep in the star to the outer layers. That's one way that you can release some of these elements. And what's cool is we've talked about the nuclear fusion going on in the core somewhat. We've talked about main sequence stars. We have the helium production, we have CNO production. Um, the story that we talk about all the time is bigger and bigger stars can build bigger and bigger atoms in their core, burning silicon, burning neon, eventually getting us all the way up to iron. And um, the issue is, where do other elements come from that aren't formed in supernova? And this is where the outer atmosphere of stars are actually an often ignored production site.
Oh, that's really interesting. So what's going on there?
So our sun, in the process of going through all these different activities, is giving off neutrons. And when you give off a neutron, you are bombarding the outer layer of your star with neutrons. And these neutrons, when they hit the atom, when they hit the atomic cores of atoms in the outer atmosphere, they can build up there. And so this is a matter of, you collide those two hydrogens together in that proton proton chain, and one of the byproducts shooting off is that neutron. So that neutron goes flying out, it hits the core of an atom. Now, neutrons aren't always stable, and if you build up a whole lot of neutrons in the outer, in the atoms and in the outer part of the star, those atoms over time are going to go too many neutrons, and they're going to undergo beta decay processes where those neutrons get transferred into protons, building up a heavier element. So we're
Oh.
essentially slowly building things up the periodic table. And the way we figured this out is the existence of technetium in the outer layers of stars. And any of you who are out there who've ever had to do high resolution spectroscopy of stars, you know what I'm talking about here, because you look
Technetium? Is
at
that a real thing? That just sounds like a made up word from
it's
Stargate or something.
it
Yeah.
does. It's totally a real thing. And it's this really annoying metal atom that has all these electron shell layers that it loves to have so many spectral lines. So you're going through trying to measure your elements, and every third line, it feels like, is coming from this one annoying metal that's unstable. And its shelf life, its half life is such that you wouldn't expect to ever find it in a star, because the stuff that star was formed out of, by the time you're seeing technetium in the outer atmosphere, looking at red giants, for instance, it should all be decayed away.
Right.
It should not be there. So when you see in the outer atmosphere of a star a short lived atom, that atom had to form in that atmosphere. And this is how we figured out there are what are called S process atoms, slow process neutron capture elements like technetium, that are getting built up in the outer atmospheres of stars as these neutrons fly out and get captured. So, some of the elements that we're dealing with, not technetium, um, but many other things that we're dealing with, lead, for instance. The only way to explain these peaks that we see in the ratios of atoms in the periodic table is to see these elements as forming through S process in atmospheres of stars, getting released during the planetary nebula phase, getting released in solar winds, getting blasted out across the universe to be recycled into worlds like ours.
Right. And so the stuff that's in the core, like if it doesn't go full supernova, the stuff in the core,
It's staying.
it's staying there. And so that's why a a like the sun will eventually turn into a gigantic diamond, right? When it cools when
Yes.
it cools down and crystallizes, and you just get all these carbon atoms in lockstep with one another. And good luck chipping a chunk of that thing off and selling it. It's locked in, And so it's not available to seed another star. But these heavier elements that are constantly being constructed in the outer atmospheres of stars and then being easily blown away because that's where the solar wind is emanating. That's absolutely fascinating to imagine this stream of stellar material that's firing out into the surrounding nebula to then act as a catalyst for future stars.
And this is the way that we just don't think about atoms forming. And it's one of these things where there's so many different ways that we end up with neutrons, and there's so many atoms that can only be explained from various parts of bismuth to plutonium to even more elements of lead, where we're relying on the S process to get at the things that we see in the sky and see in our tables, chairs, and selves.
And so really any place where you're getting neutrons mushed together, you're potentially getting those neutrons decaying and turning into protons of various
And and the catch
types.
is this happens in two ways. There's a slow process, which is the one that we've just finished. Well, we've just hit on. I won't say we've ever finished the discussion.
Yeah.
Um, but there's also rapid process, which is where you have a blast of neutrons from an exploding star. But that I think is a topic for
That's
the
going to be
next
the next
episode.
episode. So people are going to have to stay tuned. Was there anything else you wanted to cover for this episode?
I think the last thing we should probably hit on is the other way that we end up with nucleosynthesis is a cosmic ray spallation, which we sort of touched on. And this is really cool because of how it affects lithium and beryllium. And it's the kind of thing that when we're looking out at the interstellar medium, we often talk about the search for super unprocessed, raw interstellar materials that represents what came out of the Big Bang. But that unprocessed material, when it gets hit by cosmic rays, this cosmic ray spallation is enriching that material. And so we actually have in the cold, dead night cosmic rays changing these clouds. Now, to be entirely fair, this is such a minute process.
Right.
It doesn't even like raise a bleep on our radar. But I think it's cool and worth noting.
And
So,
when you think about over time, over billions of years, with the enormous number of cosmic rays that are firing through the universe all the time, striking atoms, it's not zero.
it's not zero. And so when we look at these clouds that may have been enriched by like a single supernova, that enriched material, it's getting broken down as we watch, getting
Wow.
turned into these lightest elements. And that's kind of awesome.
That's really cool. All right. Well, and for supernovas, all the explosive events, that is next time. Thanks, Pamela. Do you have any names for us this week?
I do, and I forgot to open it. Oh man, I'm sorry, Susie. Susie, I'm so sorry. You may mock me fully later. I forgot to open that window. Opening that window, going to
I
that
think we
window,
only get
hoping I'm logged
one
in.
Susie apology a week.
Yeah, I'm totally breaking that rule today. I'm not even logged into the correct account. Um, guys, I'm sorry. Brain already left. Goodbye, brain. I don't know where you went. I would like you to please come back, especially before we record the next episode. I am blathering because I hate dead air. I love all of you.
It's just like this is just like watching just a train wreck or something here, just falling apart right in front of us. Get it together.
I am. I am.
Just open the file,
Okay.
read the names. It's okay. It's all right.
I'm almost to that window. I
This
am
this
at that
this
window.
dislike of dead air is interesting. I think this is a side of your personality that I wasn't familiar with, but
Okay, so here we go. We're here thanks to you, wonderful humans who have the patience to not just be listeners, which I don't think really requires any patience, but you actually like go to the internet and go to patreon.com and support us, which means we can pay Susie. And this is a good thing.
Yes, Susie
And
appreciates.
so I want to thank Jason Graham, Brett Peterman, Anut Sar, Donald Mundus, William Jones, Father Prack, Scott Bieber, Bart Flaherty, Andrew Stevenson, Kenneth Ryan, Jason Smartsky, Matthias Hayden, Martin Dawson, Russell Petto, Dan Lightman, Glenn McDavid, and Benjamin Davies. Each week we thank a group of our patrons, and you're the ones that came up this week. And we are so grateful that you're part of our community.
Thank you, everybody. And thank you, Pamela. We'll see you next week.
See y'all. Bye-bye. And
Okay.
now we save.
So we're going to shut this down now, and then we're going to start up another stream. So you're going to need to watch for that. I'm sure somebody will put the link where that's going to be. So normally we stick around and answer questions, but now we're going to shut this down and we will reappear somewhere else. Hopefully you'll be able to find us and join us. All right. Thanks, everybody. We'll be back in a second. Let's see if I can make this stop.